Okay, previously we briefly went over the last section. I introduced the concept and rather briefly explained the results of several important theorems. In this lecture, we are going to fill in with more details to those important results. Okay. The first one is an example. Okay, I will show you how to solve this example. In this example, we know the probability function of x. It can take 0, 1, 2, 3. Or actually, it does not take 1. The probability of 1 is 0. So you can cross it out. Now we want to find the twofold and the threefold convolutions of x. Okay, let's do twofold. The way I recommend you to solve this question, at least at the beginning, okay? What I would suggest you to do is to do a two-way table. So let's say this is x1, this is x2. I'm trying to compute the twofold convolution. It can be 0, 1. Okay, so does not need to consider 1 because it cannot be 1. 0, 2, 3. So the horizontal row is for the x2 and the vertical column is for x1. The table may be a little bit small. I'm trying to fill in everything, okay? So the first field I'm going to fill is 0 because that means x1 is 0, x2 is 0, so the summation is 0. Next, I need to get the probability, right? Because we assume x1 and x2 are IID, so they are independent. In order to know the joint probability, we simply times them together. So it's going to be 0.1 times 0.1. Now let me first erase those. So it's 0.1 times 0.1, so I get probability is 0.01. Okay, going to the next cell, the summation is obviously 2, and the probability is 0.1 times 0.4, so 0.04. As similarly, we know the summation is 3, and the corresponding probability is 0.05. Okay. For the same reason, I believe you can fill all the tables, right? Once you fill all the tables, we can write down the probability function for x1 plus x2, which is the twofold convolution. Okay, sometimes we may use this notation, right? That means it's simply the convolution of two identical copies of x. So you need to discuss all the possible values. It's possible you take 0 with probability 0.01. There's no way you get 1, okay, but it's possible that you get 2. There are two opportunities. The first one is here, 0 plus 2, 2 plus 0, and the probability is 0.08, right? And the next one is 3, okay? It's 0 plus 3 or 3 plus 0. So here you have probability 0.1, right? So I believe you can continue this. Finally, we have 6. Okay, that means you have 3 plus 3 is quarter. Okay, so this is the probability function of it. Once you have the twofold convolution, you can continue to do the threefold, right? So similarly, you can get a two-way table, except right now it's x1 plus x2 as the column, and you leave x3 as the row. Okay. If I use a different color, I'm going to change this to x1 plus x2. I'm changing this to x3 if I'm calculating the threefold. Okay. So the row stays the same. But for the column, I need to expand 4, 5, 6, right? And everything else, it's pretty much the same, right? So 0 right now, the probability is no longer 0.01. it will be the probability of twofold, which is 0.01 times 0. So here it becomes 0.001, right? So etc. So you can continue. If you have the textbook, it's example 1.7. Please complete this example. So with all the hints I gave you, I believe you should be able to complete this example. But nevertheless, let me know if you can't, okay? Next, we want to show this very important theorem. Basically, we rely on two things, two properties. One, conditional expectation is a random variable. Two, if I take expectation on conditional expectation, I get unconditional expectation. Okay, with those two in mind, we can easily prove. We can pick up what I wrote. So the first identity is nothing but the definition, right? So let me equate first. So this identity is by definition. It's by the definition of moment generating function. The second identity is because of the definition of compound distribution, right? So that is the definition of S. So again, it is by definition. The third equality is by this Taylor rule. Okay, I condition on N. Now let's continue. Okay, once I condition on N, the inside part, I can treat it. I can treat now N as constant. So now with N being conditioned, I can roughly treat it as a constant. Okay, since it's a constant, what do you have? It's nothing but the because they are independent now, so it's the product. Okay, from there, what do we have? So what we have is the, so from there we can derive it is nothing but the inside part is nothing but the moment generating function of x. So this is mx of t. And because we assume they are IID, so inside part is this. Okay, as I mentioned, this is a random variable of n. From the inside part, we easily see this is a random variable of n, right? Okay, now I will need to compute this form. That means I apply the definition of n. Well, it doesn't matter whether n stops at somewhere or not. We can simply write the general form from 0 to infinity. If it stops at certain number, then after that number, the probability is nothing but 0. Okay, so here what we have is mx t to the power of n. Okay, now I need to know the probability of n equals small n. Okay, by the way, this is how we define expectation, right? Okay, from here, I just need to do one more manipulation on this item. Okay, I write it as an exponential function. If I write it exponential, I will need to take logarithm for the entire term. So my n will come out. Okay, I can write log mxt. By the way, I treat them to be the same. So the natural logarithm, okay, times. Okay, now I recall the definition of moment generating function. For instance, I can look at it here. So I know this is the moment generating function of n evaluated at log mxt, right? So I just proved this result. Okay, the moment, the probability generating function can be proved in a similar fashion, right? So if I switch to a different color. So basically what will change? At the beginning, you have let me erase this to, so the probability generating function is t to s, right? So we know we're going to do double explanation. So inside it will be e, not e, excuse me. So it's t to the sum of from 1 to n xi given n, right? So I believe it's pretty much the same. So please complete this. Okay. Again, you know, it's a little homework to you. So now let's do example. Okay. In this example, we will apply the theorem 5. So the formula of moment, the probability generating function. Okay. So now I have a Poisson distribution as the primary, geometric as the secondary. I want to know the probability that s equals 0 and the probability that s equals 1. Okay. So let me try two different methods. Okay. The first one is somehow standard. You don't need to think because we know the formula between probability function and the probability generating function, right? So in order to know the probability at each value, we just need to get the PGF and do suitable differentiation and evaluate at 0, right? That's all we need to do. And this method always works, right? So sometimes it may not be the best, and that's because comparisons can be complex. Let's see whether this is the case here. So first, I want to know the PGF of a Poisson distribution. So if you can memorize, that's good. If not, you should be able to quickly derive this result. So deriving MGF, PGF should be straightforward, especially for Poisson. Now I have geometric. Okay, geometric, I know the result is theta divided by 1 minus theta times t. Okay, so obviously t cannot be 1 over 1 minus theta, right? Otherwise, you know, you are dividing by 0. So t is not everything. So, but usually, again, you know, we are in the application side, right? So we are not always 100% correct. By theorem 5, we know the probability generating function of S. By the way, S, let me repeat the definition again, okay? And those xi's are I, D. They have the same distribution as X. So this is always the setup when we talk about compound distribution, okay? So please remember this default setup, right? So it's often the case I don't specifically say this setup, okay? But we always assume that. So by theorem 5, we know this is Pn of Px. Okay, now I can write it as lambda times, so I'm going to replace t by Px. So by the substitution, we easily get this result, okay? Now we have the probability generating function. So all we need to do is to, of course, for 0, we don't need to differentiate, right? So evaluate this value at 0, that gives me the probability at 0. So plug in 0 for t, I have exponential of lambda times, here will become, plug in 0 is just a theta minus 1, okay? Remember, theta is always between 0 and 1. So what I have is a negative number. Exponential of a negative number is between 0 and 1. That's perfect because I'm looking for a probability, right? Probability is supposed to be between 0 and 1. So this is indeed between 0 and 1. So excellent. Okay, in order to calculate the probability at 1, I will need to differentiate once. Okay, now that's the first order derivative. Well, this is in exponential form, right? So exponential stays the same when I differentiate, okay? The next part is the chain rule. So constant factor will stay. Now I'm going to deal with the inside part, okay? Again, this is a function of t. It's in negative power, so I can square the power form. That will bring out -1, right? Of course, theta will stay. And finally, I do the second layer of chain rule, right? That is the inside part. That gives me -1 times 1 minus theta. Okay, collecting everything, that is lambda theta, because I have two negatives, they will cancel each other. So I have 1 minus theta times t and square the entire thing. Okay, so finally my fs at 1 will be ps prime at 0 divided by 1 factorial. Okay, please remember to divide by the factorial. So here is 1, so it doesn't matter. But if you go to 2, you need to divide by 2 factorial, which is 2. So if you forgot to divide by 2, you would get something that is double what you're actually looking for. So the first part we already know, right? So we repeat the first part. Okay, then we have lambda theta times 1 minus theta. Okay, it's preferred to write this in front of the exponential. Otherwise, sometimes it could get a little confusion to see whether this is with the exponential or not. So it's better to write it differently. So it's better to write this in front. Okay, then I write the exponential term. Okay, I labeled this method 1. That obviously means there's another method. You can call this method somehow direct probability analysis. So this is nothing but the probability of s equal to 0. Okay, how do I get probability to be 0? There are a few things, right? So I need to discuss on n. N is a Poisson random variable. So n can be any non-negative integer. So n can be from 0 to infinity. Okay, and for n equals to small n. So if I already know n equals small n, in order to get s to be 0, I will need every xi to be 0, right? And the n of them, they are independent. So what is the likelihood? The likelihood will be simply taking theta to the power of n, right? This means all my x's are 0. Again, it's geometric, right? 0 means I don't wait. The very first trial is a success event, and I know the probability of seeing a success event is theta. That is why I raise the power to n, because I want all n x's to be 1, right? So or to be 0, excuse me, because here is the weighting. So I want all of them to be 0. So it's the first thing I see is success. Okay, and I also know the probability of n equal to small n is e to negative lambda times lambda n over n factorial. Okay. So now the question boils down to figure out this infinite sum. So it's the summation of n. So let's quickly collect similar terms. So this I can actually factor out because it has nothing to do with n. So the part with n is this, right? So if you still recall the Taylor expansion result of exponential function, you easily see this is exponential to lambda theta. So I can factor out a lambda. Okay, so of course this is exactly what I have done here, right? So it's exactly what I have done here. So they are the same. So if I use blue color to So this is exactly the same as I get down here. So checked. Of course, you can do the same thing for S1. So first of all, I discuss for every possible n. Now I don't want everything to be 0. Now I want s to be 1. Okay, so s to be 1, which means one of them is 1, right? So xi is 1, and the rest xj is 0. J is not to I, right? So that's the analysis. Now I want the summation to be 1, okay? And all my x's, they are non-negative integers. So the only scenario that I will get 1 is 0 plus 1, right? So I only have one random variable being 1, and all the remaining random variables will be 0. So what is the probability? I don't know which x is 1, right? So I need to pick 1. I have n choices. I need to select one to assign value 1 to it, and the remaining will be 0. I already know the probability of 0. So this is n minus 1 of x's are 0. The remaining one is 1, and I know the probability of it. So the first one is a failure. The second one is a success. Okay. This part is the same. Okay. Now we can do the analysis. Okay. Let me use a different color to do a little calculation. So this is n. So this n will cross this n factorial. It becomes n minus 1 factorial. Okay. Obviously, when n is 0, this thing is gone. So you don't need to discuss 0. So we can start with 1, because when n is 0, s is 0. It cannot be 1, right? So we can start with 1. Now I can factor out everything. So this has nothing to do with n. I have theta down here. Let's take out one lambda. So I will get lambda theta times 1 minus theta. Now I have the summation n from 1 to infinity. And now I have lambda. So now the current power term is n minus 1, because I have already factored out 1 lambda. So the reason is because my denominator is n minus 1 factorial. Okay. So now what I do, I can use something to replace n minus 1. Let's still use n to replace it. So now my n will begin with 0, right? So the last term is, oh, I forgot. There's another theta, my mistake. So there's another theta to n minus 1. So eventually what we have? We have exponential lambda theta minus 1 times lambda theta 1 minus theta, which equals what we have done here, right? So they give you the same result. Obviously, that's what we expect. Pania recursive formula. Unfortunately, this is one of the few formulas that I don't have too much insight, but rather ask you to memorize. Okay, but of course for this course it's open book exam, so it's ordinary issue. But for SOA you do need to memorize this formula. Now let's prove this. Okay, the first result it's straightforward. Okay, it's actually something we anticipate. So I just quickly show you this result. So first step is by definition. This is how S is defined. Next, I condition on big N, because that is the part causing the issue, right? So when big N is a constant, I know the inside part is, so using this notation, is the expectation of X times the number to be summed, right? So here we condition on N, so we treat N as a constant. Now, this is a constant, so right. So the first result is easy. Okay. For the second result, I can actually write it in this way. So we know S is in this form, right? And the variance of S somehow takes a symmetrical tree. So this equals the expectation of conditional variance plus the variance of conditional mean. I believe this is more hopeful to memorize and is in a symmetrical term. The variance or the unconditional variance of S equals the expectation of conditional variance plus the variance of conditional mean. Okay, so let's prove this. So obviously this is the expectation of S squared minus the square of expectation. Okay, so that everybody knows. And then I will apply Taylor rule to the first square term because that is the part giving us the problem. Okay, for the inside part, for this particular part, okay, we apply the definition of conditional variance. Okay, conditional variance is basically the same as variance except everything is given the condition. So by the definition of conditional variance, this is the conditional variance plus the square of conditional mean. So as I said, conditional variance is defined as the conditional second moment minus the square of the conditional expectation. So the definition is basically symmetrical to the unconditional version. Okay, now let's introduce y for this guy. Then I have expected value of conditional variance. Okay, so I already have the first guy. Now what I have is expectation of y squared minus. So I apply Taylor rule to this. I get double explanation, right? According to my notation, the inside part is y. So I can write this as expectation of y squared, right? So now you see this is the variance of y. And the variance of y is, well, now I write back the definition of y. Okay? So I just proved this very important result. Of course, we are one step away from that. So once I condition on n, I treat n as constant. Right? So this is the conditional variance. Because I treat n as constant, so the inside conditional variance, so basically sum them up because they are independent, right? And there's n of them. Each one has variance sigma x squared. Now I have n of them. That's why it's n times sigma squared minus the variance of n times the expectation of x, right? So let me erase this so that does not confuse you. Okay, again, I simply treat n as a constant when I take conditional expectation. Then what I have is the number of x's, which is n, times the expectation for each one. So finally, here sigma x squared is a constant. So it's mu n times sigma x squared. And obviously mu x is also a constant, but now we are taking variance. If we are taking variance, that constant has to be squared. So this becomes mu x squared. So this is this formula. So my personal suggestion is remember this. And technically, you know, I just showed you the proof. So it's not entirely impossible to understand the proof. If in case you have trouble understanding the proof, remember this symmetrical form. Okay, it always works. One special case is when n is Poisson. When n is Poisson, mu n equals sigma n squared equals lambda. So in this case, the variance of S equals lambda times the expectation of x squared, because I can collect this plus this. This is nothing but the expectation of second moment. So this special formula, it's very helpful because we often apply a Poisson distribution to model the primary distribution. Okay, I will stop here and we'll continue in the next video.